Okay, this is Mr. Peterson, and we're going to be looking at problems 7 through 10 in the Chapter 2 review, Part B of Chapter 1's review. And we're supposed to solve by the substitution method, it tells us here. So I've set them up side by side. That's my favorite way to set it up with substitution. You'd be wise to do the same. And we're going to look for a place where you have a 1x, that wouldn't be here, or a negative 1x, there we go, or a 1y, and we don't have either that or negative 1y, so I'm going to start with this negative 1x. That's the variable that you want to get by itself. So we'll start on this right side over here, and I'm going to solve for that x. Subtract 4y from both sides. Now I could write, let me show you, I could write divided by negative 1 here, divided by negative 1, and divided by negative 1. Maybe that'll be more understandable, but there's a shortcut when you do that. If you divide everything by negative 1, you just change all the signs. And now that expression, 4y minus 23, we know that's the same as x. So we can come over on the other side and substitute in place of that x the expression 4y minus 23. So you carefully replace the x with 4y minus 23. Distribute here, and you'll get 20y, and then 5 times 23 is 115. We'll add 115 to both sides, and while I do that, I'm going to put these two together here. So since they're like terms, 20y minus 2y is going to give 18y. And on the other side, we get negative 25. That was already over there, plus the 115 that we're adding to both sides. And 115 minus 25 is 90. So we'll divide both sides by 18. And that takes us to a y value of 5. So now we simply substitute on the other side, and you get x is equal to 4 times the new y value that we now know is 5. And that tells us that x has to be 20, take away 23. In other words, x must be the number negative 3. So now you just put it in the right order. X goes first when you're plotting points, and these are points, and 5 is your y value, and that goes second. So your answer is negative 3, 5. Okay, another one like that, except this one's a little less convenient. You'll notice that we don't have a 1x or a 1y or a 1x or a 1y. So this would really normally be a problem I wouldn't use substitution on, except if you really play your cards well, you can find a place where you can get one of the variables by itself without resorting to fractions. Now I'm going to start by showing you one that would be a poor choice. If I wanted to get this x by itself, eventually I'd have to divide everything by 5, whether I do it now or later. But you can see this 4/5 and negative 8/5. Those are really fractions we'd rather avoid. So you look for a coefficient that when you divide it through the problem is going to give you non-fractional answers. And it's right here. If you divide everything by 3 here, you end up with what we're looking for at the start, in this case a 1y. And you can see that when I divided everything by 3, I chose that one because I knew I wasn't going to get any fractions. And this is a lot easier because of that. So I'm going to take that variable over to the other side, and I get 2x plus 11 is the value of y. So now I can come over here, and now that I know the value of y, I can replace it. So 5x is already over there, plus 4 times the value of y is equal to negative 8, and the expression we have is 2x plus 11. We'll distribute here. Collect our like terms. The next thing I'm going to do is subtract 44 from both sides. And if you divide both sides by 13 here, you get negative 4. Simply substitute that back on the other side. So if you've been paying attention, there's actually 2 substitutions involved in these problems. The first one is, on this example, was when we went and substituted that on the other side. And then we took the answer we got and substituted it back on the other side again, the original side. So we finally end up here with an x value of negative 4 and a y value of 3, and that is the point where these lines would intersect. So there's your solution. Okay, what we're going to encounter on these next couple of problems here, I guess I'm not sure what we're going to get yet, but there's going to be some of the exceptional cases, parallel lines, for instance, that will probably show up in one of these problems. All right, so let's solve for the 1x. You can see there's a 1x there. And if at all possible, that's how you start these problems. I'll substitute for x when I come over. So I've got my negative 6y and then minus 2 times the x value equals 30. And we're going to be using negative 3y plus 12 here. So that takes us, when we distribute here, to negative 6y plus 6y minus 24 equals 30. And you'll notice on this one that the like terms cancel off. They give 0. So we end up with an impossible situation. 24, negative 24 is supposedly equal to 30. That's never true. And this is the hallmark of parallel lines. So that's what we're dealing with here, parallel lines. Please notice how parallel is spelled. There is no solution to this problem. And this is usually referred to as an inconsistent system. Okay, let's do another example of this. This is example H. And I'm looking for either a 1x or a 1y, and the closest I can get is up here. There's a negative 1x. So I'm going to start by changing all the signs in the problems. And that would be equivalent to dividing everything by negative 1, or maybe even multiplying throughout by negative 1. But now you can see that when I haul this over, I get an expression for x, which I then substitute for x over on the other side. Distributing here gives 10y plus 30 minus 10y equals negative 30. I made a mistake, and let me fix it. You probably noticed it. There should be a negative in front of that 15. And I apologize for that because I might have thrown you off. So let me do the fixing. Like that. And the 10y minus 10y cancels off since it gives 0. And here you get a statement that's always true. Negative 30 equals negative 30. So that's always true. And this happens when you have what's called a dependent system. It's coinciding lines. You get infinitely many solutions to this one. And this is a dependent system. That's what it's called. Okay, one more here. And what we have here is an example where you don't see a 1x or 1y anywhere. You got a 5 in front of that x, a 2 in front of this, and a 3 in front of that, and a 4 in front of that. And because of that, we would not use, I don't think there's an easy way to use substitution at all. In fact, if you look at the instructions, we're switching methods. When there's not a 1x or a 1y, you want to avoid the substitution method unless you're told in the instructions that you have to. Now I'm going to go back to one of the problems we had where there was not a 1x or a 1y. You notice this one here, I called it example F. We got around this problem by dividing by 3 here. In other words, we notice that the variable that's in front of this y divides into the other numbers in that line. But on the one that we're working on here, you can see that if we divided everything by 5, you'd get negative 3/5 over here. That wouldn't help us. If we divided everything by negative 2, we'd have a nasty fraction. If we tried to divide by 3 to get the x by itself here, you'd have, for instance, 4 over 3, and we don't want to deal with that fraction. And likewise, if you divide everything by 4, you would have problems there too. So we are going to back up and follow the directions. It says use elimination. And I'm going to come back and show you how to do this on the next video. This is actually this next section.